All right, this is slide number 2 or video number 2. This is on the group properties of the elements. So the two big groups are the metals and then the nonmetals. So in the nonmetals, we're going to start there. They are not ductile. That means that they don't bend easily. They're kind of rigid and they tend to break easily. They're not malleable. You can't pound on them and make them softer. They're not shiny, typically, and they don't have a metallic shininess or luster, so they won't reflect, say, like this. This is metallic. Okay. They are typically electron acceptors. That means that their outer orbitals want to collect electrons. Noble gases is the first one, and then that's that column on the far right. And therefore, it's going to fill in. It's already full, so it's not going to react with anything. So the next one over is just missing one electron, and it's extremely happy to get it. So it's going to react. And those are almost, both of these are gases. So this is like oxygen and sulfur. Now, they can turn into solids once you get down from sulfur downward. So the gaseous substances are around here too. Most gases are kind of light. And once you get below oxygen, they start becoming solids once you have more than one electron missing. Okay. Metalloids, those are the ones that kind of go both directions, can act like a metal, can act like a non-metal. They're brittle. They are also really important for electronics. Now, it's the next step to the metals. Now we're going to go into the metals. What makes a metal a metal? Well, metals are shiny, metallic, luster, malleable, ductile, electron donors mostly, and they conduct electricity. All of them will conduct electricity. Maybe some conduct electricity better, like copper is one of the best conductors. Now, in the metals, alkali is your very first group. That's the very far left group. So that's these guys here. And the alkalis are incredibly reactive. In fact, if you start putting them in water, they're going to explode. The further down you go, the more likely they are to explode. So lithium will kind of fizz. Sodium will kind of psh. Potassium will kind of burst into flames. Rubidium kind of explodes. And if you get all the way down to francium, it just goes poof. It's kind of crazy. Alkali earth group, that's the next one. They're more reactive as you go down, just like that. And once you get below calcium, they start to be highly reactive. Okay. Now we're getting into the transition metals. Those transition metals change their valence, and it depends on who they're reacting with, and the temperatures, and the moisture, and all sorts of different things will accompany that. Okay. So I'm going to go into a second one here. This is valence and structures of bonding. Now, valence is that outer shell, and the outer shell, what's it missing? Is it got too many? Is it got like one floating around? So this one here has 2 on its inner and 4 on its outer. So this guy wants 4 electrons, but will also give up 4 electrons. So that's why you'll see over here a -4 and a +4. This is the Bohr model. The protons and neutrons are the only number that protons and neutrons do not always equal. Sometimes they do, like in carbon. But how do you get the number of neutrons? Is you subtract the atomic mass minus the atomic number, and whatever you're left over with, the whole number, is the number of neutrons. Okay. Bonding. Why do they want to bond? Well, there's ionic bonds, and ionic bonds are usually a metal and a non-metal. One gives up, one accepts. Those are the strongest. Then you have covalent bonds. That's like if 2 carbons were to stick together and they share their electrons, or 2 oxygens is very common to stick together, and they'll share their electrons to fill up the outer 8 in that orbital shell. That group of 8 is one of those really important things. So ionic is strongest. Covalent is usually nonmetals combining. Polar bonds, now when you have these nonmetals combining, sometimes if they're not symmetrical or uneven, they end up having a polar end. Like water will set up at an angle like this, and the reason is the 2 oxygens don't want to get 2 hydrogens don't want to get close to one another, and that weights one end of it to become polar. Hydrogen bonding is if there's hydrogens available, they're going to be making a little bit of a sticky bond because hydrogen only has one proton. It's going to react with stuff, and that's the nature of making those stickier than normal. And then van der Waals bonds, which we're not going to go into at this point at all. Just know that they exist. Okay, and that's all.